Hey, this is going to serve as a way to review the more complex modeling problems. We're going to start with the mixing tanks, and we're going to start with this problem. Consider the large mixing tanks shown below. Suppose that both tanks A and B initially contains 100 gallons of brine. Brine is a mixture of water and salt. Liquid is pumped in and out of the tanks as indicated in the figure. The mixture is pumped between and out of the tanks is assumed to be well stirred. Okay. So they're assuming that the concentration in the tubes is the same as the concentration in the tank. So A, construct a mathematical model in the form of a linear system of first-order differential equation for the number of pounds x sub 1 of t and x sub 2 of t of salt in tanks A and B respectively at time t. Write the systems in matrix form. So to do that, we'll focus first on tank A. So for tank A, what we're going to have is, let's see, for tank A, we're going to have that the amount of salt, the rate of change of the amount of salt with respect to time is going to be equal to the rate in minus the rate out. So let's see if we're able to write this. So what is the stuff that's coming in? Well, we got stuff coming in here and here. So we have 2 gallons per minute coming in. And remember, this is the amount of salt in pounds with respect to time in minutes. So this has units of pounds per minute. How do we get units of pounds per minute here? Well, we have to divide by gallons and multiply by pounds. Now, this is the concentration of salt. How much salt is coming in from that left top side? Well, it says it's pure water. So there's a 0 concentration of salt. There's 0 pounds of salt per gallons. So we can write this. And now we're going to look at the top right. And we have 1 gallon per minute coming in. So we're going to add 1 gallon per minute here. And we're going to multiply by the concentration in that tube, which is connected to this. And it's well stirred, which means that it's going to be whatever concentration is in B. Now we're saying in B, we have the amount of salt in B at any one time is x sub 2. And it's divided by the total amount of gallons in tank B. Now we said there's 100 gallons in tank B, right? It said that in the problem statement above, initially contain 100 gallons. And then notice we have 2 gallons going in here and 2 gallons going in here. So a total of plus 4 gallons per minute going in times time. So depending on what time it is. And 3 gallons going out and 1. So a total of minus 4 gallons per minute going out times time, which means that these are going to cancel out, and there's always going to be 100 gallons inside that tank. So this is just for the rate in. Now we're looking at the rate out, the bottom left for this left tank, and we have, sorry, I indicated on the right tank before when looking at the overall rate going in and out, but I wanted to do it for the left, which also happens to have a constant amount of volume of 100. So for both, we're just going to write 100 at the bottom here. Now going out, we have minus 1 gallon per minute at the concentration of A, because that water is coming from A, divided by the volume of A, which we said just now is still 100 gallons. And then we have minus this other one coming out, which is 2 gallons per minute, times again the concentration of A, because that water is coming from A. Now we're going to simplify what we have over here. So this will be 0. This will be x2 over 100. Here we'll have x1 prime minus x1 over 100. But we can combine it with the other one. So we can say minus 3. See, because the gallons here cancel out. And then we have x over 100 minus 1x over 100 minus 2x over 100, which is minus 3x over 100. So in total, this is the model for our tank A. The same thing can be done for tank B. So for tank B, we're still going to have that model, x sub 2 prime is equal to rate in minus rate out. So what is that? Well, now we see that the stuff coming in is 2 gallons per minute at the bottom and 2 gallons per minute at the top. Let's start from the top. 2 gallons per minute at what concentration? Well, it tells us at a half a pound per gallon. So times 0.5, or let me write the 0 in front, 0.5 pounds per gallon. And then we have something else coming in from the bottom, 2 gallons per minute at the concentration. Well, that water is coming from this A, so that's going to be the concentration of A, which is x1 divided by 100. Okay, and now we're going to have the stuff that's coming out of it, which is going to be what? It's going to be 3 gallons per minute at the concentration of the tank in B, because that's where the water is coming from. So here we have gallons and here we have gallons. And then we have this one at the top, which is 1 gallon per minute at the concentration, again, of the tank B, because that's where the water is coming from. So now I can simplify all of this and I can say 1, this cancels out, and I can say 1 plus 1 over 50, because this becomes 50 and this becomes a 1. So what is 1 plus 1 over 50? Well, we can say that that's the same thing as 51 over 50, right? 50 over 50 plus 1 over 50 is 51 over 50. So here we're going to get 51 over 50. I'm going to drop the units, x1 minus 4 over 100. So what is 4 over 100? All right. So we have 51 over 50 x1 minus 1 over 25 x2 right here. And that's going to be x2 prime. And assuming we did this correctly, now we can rewrite the whole system. I'll switch color, and we'll have x sub 1, x sub 2 prime prime equals, what do we have? Well, we need to put the x1 first. So we'll put 3 over 100 and 1 over 100, and then 51 over 50 and negative 1 over 25. And here we're going to have x1 and x2. This one, some people might be confused about this step, but if you multiply it out and execute the matrix multiplication, you'll get these two things. Just maybe you'll have this term here, but it's still the same thing. So this is our model, and I think we have fulfilled the request of part A. All right, I'll see you later for part B.